This is Dr. Mark Barkey, and this is the class AEM 637 Theory of Elasticity. My email address is mbarkey@eng.ua.edu, and you can also contact me by telephone. So, this is going to be a class in the theory of elasticity, and we'll discuss what all that means. And some of this will make more sense as we get into it, but we have some specific course objectives that we want to accomplish by the end of the semester. We want to be able to properly use tensor notation or index notation. We want to be able to read and summarize a technical paper in the literature. And we want to be able to know the basic tenets of continuum mechanics, basic definitions of stress and strain, and various applications of the theory of elasticity. Now, typically, a fairly diverse group of students will take this class. There may be students in civil engineering, usually graduate students, civil engineering, materials, mechanical engineering, mechanics, aerospace engineering, and so forth. And because of that, we'll look at a variety of applications, but this class will be fairly mathematically based. Okay, so we're gonna have some math, and it'll be based on classical solutions. And one of the things that's kind of happened over the years, and we'll talk about when elasticity started, one of the things that has happened over the years is that theory of elasticity has evolved from closed form solutions to being more of a numerical field. And you may use something called finite element analysis, which is basically a numerical way to solve boundary value problems of elasticity or plasticity. Now, in theory of elasticity, we'll take a look at from the more classical approach, where we look at classical boundary value problems of elasticity and try to solve them. Now, to put this in some perspective, you probably won't be asked to solve new boundary value problems of elasticity. You might, but it's at the point where it's fairly unusual to have a new class of problems in elasticity these days. However, with the background that we're going to go over in this class, you're going to have a deeper understanding of mechanics in general and applications of applied mechanics for various applications in elasticity, plasticity, fracture mechanics, and of course, continuum mechanics as well. So, in a way, it might be interesting for you to think of this class as sort of a liberal arts education in classical mechanics, as opposed to something that you're going to go out and use every day. That said, the things that we'll go over are very interesting classical solutions that are used fairly frequently still and form the basis of a lot of design guidelines. So we'll approach it from that perspective too. Now, we have a book that I've picked out. It's Elasticity in Engineering and Mechanics, third edition by Barisi, Chong, and Lee. However, I'd like to read a little bit of information from you from a classical elasticity book. Elasticity, if we really go back, can go back to the investigations of Galileo and then Newton. Um, in those time periods, there were some advances, but things really started getting going in the 1800s. There was a lot more industry. The railroad industry was taking off, and people were interested in solutions of stresses and all kinds of different things: springs, railroads, foundations, plates and shells, and all this. People started looking at those in the late 1800s. I want to read to you from a book called The Mathematical Theory of Elasticity by A.E.H. Love. It's kind of a classical mechanician. So let me call that up on our screen. Now, this book can be found on our course. It's old enough that the copyright has expired, and it's kind of interesting. The one I'm going to read from is the fourth edition. And this is a particular handout that I've got. And what I'm going to read to you is this information I have marked. And it says, for historical introduction, the mathematical theory of elasticity is occupied with an attempt to reduce to calculation the state of strain or relative displacement within a solid body which is subject to the action of an equilibrating system of forces or is in a state of slight internal relative motion and with endeavors to obtain results which shall be practically important in applications to architecture, engineering, and all other useful arts in which the material of construction is solid. Okay, so one of the things that you'll notice is that the way sentences were written a number of years ago is a little bit different than what how we write sentences today. Fairly lengthy sentence, but what it's saying is theory of elasticity is for things in equilibrium, okay, or could have a state of slight internal relative motion, and it's trying to find results that will be practical for architecture and engineering and things that are made out of solid materials. Okay, so in mechanics, we kind of have a division between solids and fluids. We have some other divisions as well. We'll go over those in a little bit. Um, but for this class, we're going to look at solid materials. Now, initially, we're going to approach the class as in the form of general continuum mechanics, which will also be applicable to fluids, but then we'll specialize it to solids and so forth. All right, so let's read the next sentence. Its history should embrace that of the progress of our experimental knowledge of the behavior of strained bodies so far as has been embodied in the mathematical theory. Zoom in a little bit. Of the development of our conceptions in regard to the physical principles necessary to form a foundation for theory, the growth of that branch of mathematical analysis in which the process of the calculations consists, and of the gradual acquisition of practical rules by the interpretation of analytical results. All right, so we're going to study elasticity from the perspective of mathematics. We're going to develop a mathematical theory that's grounded in physical principles, and we're going to uh, gradually acquire practical rules for the interpretation of analytical results. So we're not going to come up with things that don't make sense. The things that we come up with will make sense from a physical perspective. In a theory ideally worked out, the progress which we should be able to trace would be, in particulars, one from less to more. But we may say that, in regard to the assumed physical principles, progress consists in passing from more to less. So you may be familiar in physics that there's always trying to come up with grand unified theories of physics. And that's the idea here. And really, that idea started a long time ago, in which you're not trying to have more and more special theories come about, but what you're trying to do is to have certain basic fundamental physical principles that can be applied very broadly. And if you have fewer physical principles, then you have been making progress in your theory. Alike in the experimental knowledge obtained and in the analytical methods and results, nothing that has once been discovered ever loses its value or has to be discarded. Okay, so if we do some tests and they're good tests, then we need to keep that knowledge and make sure our theories conform to that knowledge. But the physical principles come to be reduced to fewer and more general ones, so that the theory is brought more into accord with that of other branches of physics, the same general principles being ultimately requisite and sufficient to serve as a basis for them all. And although, in the case of elasticity, we find frequent retrogressions on the part of the experimentalist and errors on the part of the mathematician, chiefly in adopting hypotheses not clearly established or already discredited, and pushing to extremes methods merely approximate, and hasty generalizations, and in misunderstanding of principles, yet we observe a continuous progress in all respects mentioned when we survey the history of the science from the initial inquiries of Galileo to the conclusive investigations of St. Venant and Lord Kelvin. All right, so he's taking a little bit of dig at the experimentalists and some of the mathematicians. Uh, he could himself be considered a mathematician. And that is, you can have errors, and those will happen. You can make some bad assumptions, and those can happen in your theories. But when you carefully look at it, if you treat things carefully, then we're going to have a continuous progress in continuum mechanics, basically. And it's been continuous ever since those initial investigations of Galileo and I guess, more of his contemporaries, St. Venant and Lord Kelvin. Okay, so the whole book is available, and it has some interesting solutions. The problem with using this book in this class is, well, you see, it's not an easy read, and the notation is a little bit outdated as well. It's good notation. It's just notation that people don't use as much. So I'll let you read through that and take a look at that in more detail if you would like. And we may even investigate a solution or two that come out of Love's book. Let's talk a little bit about mathematics and mechanics in general. And I'll bring this handout over. This is also available. And this is a mechanics class. And what mechanics is the study of how bodies respond to load. So there are many different branches of mechanics. So over here I have continuum mechanics, and they kind of go hand in hand with applied mathematics. Over on this side, on continuum mechanics, we have solid mechanics, which, among other disciplines, can encompass the study of elasticity. What we're going to study, the study of recoverable deformation, plasticity, which is irrecoverable deformation, doesn't go back to its original shape, fracture mechanics and finite elements, fluid mechanics. We have classical fluid mechanics and boundary layers and viscous flow and turbulent flow and so forth. We have more of the structural behavior side of things, looking at dynamics, dynamics of particles, rigid bodies, and flexible bodies. And kind of going along on the other side with applied mathematics, solid geometry, probability and statistics, tensor and vector analysis, ODEs and PDEs, and numerical methods, including finite elements, genetic algorithms, and CFD, computational fluid dynamics. And so all these things kind of evolved together in about the same time. And I always think it's kind of interesting to think of the historical context of the material that we're learning, in addition to just learning the material, because you see what the items, the topics of the day, help drive what people were interested in. Right? So there are some new areas, relatively new areas of mechanics that are being looked at today. The new areas are micromechanics and material science, or subcontinuum scale, or some people call it the mesoscale. We'll talk about what a continuum is and what length scale that we need to be, but there are things that just don't behave the same way at a very subcontinuum length scale. You can even go down to quantum mechanics if you would like, study of atoms and parts of atoms. Above that, we have MIMS, micro electromechanical systems. So it's a combination of dynamics, electromagnetics, and solid mechanics, maybe even fluid mechanics too, depending on what the MIMS device looks like. And we can also incorporate elements of modern physics in a lot of mechanics these days. But a lot of the principles will still go back to classical mechanics, concepts of equilibrium, acceleration, mass, conservation of mass, continuum mechanics. A lot of things will still go back and use a lot of those concepts on a global or macro scale. So there are certain analyses now in engineering. We still don't quite look at individual atoms, but we do look at groups of atoms, and there are things called ab initio analysis. You might use something like that for taking a look at groups of atoms. Polymer physicists, chemists, and engineers will sometimes use something called LAMPS, which is taking a look at groups of molecules that interact with one another. Okay, and on this page, gives you a little bit of idea of when classical physics came about and modern physics came about. Classical physics, I'll put a number at about 1500 to present. Galileo and near that time. But we typically have optics and mechanics as two branches of classical physics. Study of light was very important, it still is, as well as the study of mechanics. And then we have modern physics, which I'll put at about 1920s to present. We started to get into electromagnetics, particle physics, and quantum mechanics. So our things that we're going to learn about typically will be uh, Newtonian type physics, the classical physics. However, like I mentioned, there are some applications where we can take some of our ideas and incorporate them into more modern physics. And in fact, as we get along into the course, we'll see that some of the great discoveries of Einstein seem to me to be very much based on continuum mechanics. As far as the math goes, geometry, calculus, we mentioned some of these differential equations, partial differential equations, variational calculus, statistical analysis, probabilistic analysis, and the calculus of tensors will be some things that we'll touch on. Now, you may not have classes at the advanced level on all these different topics that we mentioned, but we're going to learn a little bit of math as we go along. So we'll continue on a little bit with our introduction. One of the things that I like to do in my classes is use kind of an outline format for my notes. And uh, the way I'm generating these notes is I'm writing on a tablet, and I'll apologize in advance, and I'll probably just say it this one time, but I'll apologize in advance that it's not a PowerPoint type presentation that I'm giving you, because we're going to do a lot of mathematical manipulations. And if I just throw up an equation and I don't show you how we get to it, then it's going to be kind of hard to follow along. Now, the downside of that is when I do have to do a lot of writing, it may look like it's not as nice as if I were to have typed it out. And again, I'll apologize in advance for that throughout the semester. Um, but this is what we have, and if we need, I can go back and I can type some things up as I have time. But right now, what we're in is our course introduction. We've talked about mechanics in general, which is the study of how bodies respond to forces, and we talked about its relation to physics and mathematics. We've talked a little bit about what elasticity is, and we can define that as the mathematical study of materials and structures that experience recoverable deformation. Initially, we're going to take the point of view where we're not distinguishing between permanent or recoverable deformation. So we'll start from the point of view of general continuum mechanics, but soon enough we'll specialize all of our equations and our approaches to elasticity. Now there's going to be some things that our course grading is going to be based on. I won't put down the percentages in here because sometimes I adjust these, but I will give you a handout that will let you know what's going on. We will have homework, and homework will be important for our class. So that'll be a significant part of the class. We're going to have a midterm. And I usually give some sort of quiz. And I usually give a pretty good indication of what type of problems are going to be on the quiz. The type of problems that we're going to work in this class are going to be relatively lengthy. It's a graduate class. I'm not going to give you a whole lot of homework, but the homework that I'm going to give you will tend to take a little bit of time to work through. Your understanding of that homework will greatly help you understand how everything works and uh, understand everything that we're talking about in class. So that homework is very important. The midterm will probably have one or two part quiz to go along with that. Of course, we'll have a final exam in the class as well. And I also like to have some sort of participation or presentation. So I'll put that in here. Now, as a graduate class, I don't work just a ton of examples like I might work in an undergraduate class. I will work some examples, but what I like to do for the graduate class is I like to have students present their own solutions to some of the homework problems and share with the other students. The way I usually do this is with a voice over PowerPoint type presentation that you would develop. Okay, so you may need to pick up a headset or use a laptop that has a built-in microphone. But basically, kind of what I'm doing now is we go through a homework solution, and you would prepare the slides or the pictures, and then use your voice or words to describe what's going on in that problem. And we'll see some examples of that, and we'll get to that as the semester goes on. But these are the four main items that we'll have in this course. All right, so to finish up this particular lecture, some of the topics that we'll have in our semester will be this introduction and an overview. We're going to next go into some mathematical preliminaries, make sure everybody's kind of on the same page as far as the math goes. And we'll really learn it when we use it, but we need to state it up front. We're going to get first into deformation and strain. Then we're going to look at stress and constitutive relations, the relationships between stress and strain. We'll look at three-dimensional elasticity, 2D or plane elasticity, and then try to look at some various applications. So for next time, please read chapter 1 on the mathematics. We're going to go over some of that. We won't go through all of it. We'll kind of go through the parts that we need now, and then rather than having a couple weeks worth of preliminary mathematics, we're going to get into our material, and then we're going to refer back to chapter 1 when we need it. But if you read it now, then you'll be in good shape for the next time. See you then.